Hi there, this is Materials Lesson 6, Exam Style Problems. Bit of a long one, but a lot of good questions in this. So, some equations first of all. So we might need these. So energy is half force times extension, half Fe. We've got energy, elastic strain energy, half Ke squared. K being the spring constant, measured in newtons per meter. And remember the E for Young's modulus, not energy, E equals Flee. We need that one as well. And the F equals Ke. So force is equal to spin constant times extension. Alright. So let's get to it. So pause and have a go. A load of 3 newtons is attached to a spring of negligible mass and spin constant 15 newtons per meter. Calculate the energy stored in the spring. So what we need to do is find the extension using F equals Ke. So extension is force over the spring constant. So we've got 3 newtons divided by 15, which gives us an extension of 0.2 meters. Then we can get the energy stored in the spring. So elastic strain energy is a half Ke squared. So that'd be 0.5 times K times 0.2 squared. So that gives us an elastic strain energy of 0.3 joules. For that one, you could have also used the energy is half Fe, which is the same answer, so it doesn't really matter which one. Okay, let's move on. So let's pause and have a go. A stone is projected horizontally by a catapult consisting of 2 rubber cords. The cords, which obey Hooke's law, are stretched and released. When each cord is extended by x, the stone is projected with a speed v. Assuming that all of the strain energy in the rubber is transferred to the stone, what is the speed of the stone when each cord is extended by 3x? So pretty straightforward. We have a loss of elastic strain energy equal to a gain in kinetic energy. So loss of strain is equal to a gain in kinetic. So the loss of strain energy would be a half Ke squared equal to a gain in kinetic, a half mv squared. Now K and M are constant, so the only thing that we're looking at is the relationship between extension and velocity. So E squared is proportional to V squared. So if we multiply this side by 3, because the extension is 3x, the same would happen to the other side. And because both quantities are squared, the 3's suffice. We don't have to do anything else. So the answer, what is the speed of the stone when each cord is extended by 3x? 3v, 3 times the velocity. Hope that went okay. Let's move on. So let's pause and have a go at this one. A wire of length L and cross-sectional area A is stretched by a distance E by a tensile force. The Young modulus of the material of the wire is E, which expression gives the elastic energy stored in the stretched wire. So what we're going to do is to take 2 equations. So we've got E equals half force times extension. And we're simply going to substitute in for force the E equals Flee. So I'll put that up here. E equals Flee equation. And then rearrange it to find F and then make substitution. So force will be equal to Young modulus times extension times cross-sectional area divided by length. And then we're going to substitute that in here. So the elastic energy is equal to a half times the force. So let's do E times A times extension, and then we've got another extension, so E squared divided by 2, because we've got the 2 there, the half, times L. So EA E squared over 2L. So the answer is A. Well done if you got that. Let's move on to the next one. Let's pause and have a go. Quite a lot in this question. Synoptic element, going back to mechanics, moments in particular. and then I'll take you through the answers. So the diagram below shows a vase placed on a uniform shelf that is supported by a steel wire. The mass of the vase is 0.65 kilograms and the mass of the shelf is 2 kilograms. The shelf is hinged at A. The steel wire is attached to the shelf 0.3 meters from A and is at an angle of 30 degrees to the shelf. The other end of the steel wire is attached to the wall. So, first of all, let's state the principle of moments. So that's straightforward. The sum of the clockwise turning effects is equal to the sum of the anti-clockwise turning effects, which ensures that the system is in equilibrium. So in an exam, I would write this and then make a note. The system, therefore, is in equilibrium. And that suffices. So, next bit. Show by taking moments at A that the tension in the steel wire is about 50 newtons. So, about A. So from this point, I'm going to write the clockwise moments is equal to the sum of the anti-clockwise moments. Hopefully I can fit this in. Keep it semi-neat. So if we start at A and go horizontal, the first thing that we'll get to is the mass of the shelf, the 2 kilograms, which would act in the centre. And the entire beam is 0.5 meters, or the shelf, uniform shelf. So the weight of the shelf would act at the midpoint, 0.25 meters. So clockwise, we've got 2 kilograms times 9.81. So 2 times 9.81. And then we need to multiply by the distance from the hinge, so 0.25. So that's the first clockwise moment. Then the next clockwise moment is the vase. So we've got the mass, we know the distance. So let's add this. So we're going to add. So the mass of the vase is 0.65. So we've got 0.65 times 9.81 times the distance. Now the entire shelf is 0.5 meters. And the vase is 0.05 meters from the right hand side, so the distance from the pivot is 0.45. That's it for clockwise. Now the anti-clockwise one is the vertical component of the tension in the cable. So tension vertical. This is the tension acts in this direction. So what we can do is that vertical tension is actually this as well. And that component is T sine 30. It's sine 30 because it's opposite the angle. So that is T sine 30 acting upwards. So the anti-clockwise moment is the T sine 30, the vertical tension. So T sine 30 times the distance to it. So the distance from the hinge is 0.3 meters. Then you just need to evaluate this to find T. So we've got 2 times 9.81 times 0.25, which is 4.905. So what do we got down here? 4.905 plus the 0.65 times 9.81 times 0.45, which is approximately 2.8694. And they are equal to T times sine 30 times 0.3. So if you do the 4.905 plus the 2.8694 divided by sine 30 times 0.3. So if I divide by 0.3 lots of sine 30, that will give us the tension. And the answer, the tension, is 51.83 newtons, which is about 50 newtons, which was asked in the question. Let's do the last bit. So in this bit, the cross-sectional area of the steel wire is 7.8 times 10 to the minus 7 square meters. The steel has a Young's modulus of 180 gigapascals. Calculate the tensile strain of the steel wire. So to get strain, we've got the Young's modulus. So Young's modulus is stress over strain. And we want the strain. So strain would be stress over Young's modulus. So strain is stress over the Young's modulus. Now we've got the Young's modulus, it's 180 gigapascals. we just need the stress. So stress is force over area. So the force is the one from earlier, the 51.83, divided by the area, which is the 7.8 times 10 to the minus 7. This gives a stress of 6.6 times 10 to the 7 pascals. So the strain is equal to the stress, 6.6 times 10 to the 7. This one's rounded, you should use the full value in your calculation. Divided by the Young's modulus, 180, times 10 to the power of 9. That gives a strain that's equal to 3.7 times 10 to the power minus 4. Hopefully that went okay. Well done if you got all that right. Let's move on. So this one, pause and have a go. State Hooke's law for a material in the form of a wire and state the condition under which this law applies. So straightforward. So force, well, F equals KE. So force is directly proportional to extension up to the elastic limits. Remember, after the elastic limit, Hooke's law will fail, no longer work. Hopefully that's okay. Right, let's move on to the last one. Quite a lengthy one, but a good one. So you want to pause and have a go. A length of steel wire and a length of brass wire are joined together in series. This combination is suspended from a fixed support and a weight of 120 newtons is applied at the bottom end. So then we've got some information. So cross-sectional area of each wire is the same, 3.2 millimeters squared. Length of the wire, 0.85 meters, and the brass wire, 1.35 meters. We've got both Young modulus, and then we've got the density of steel and the density of brass. So first of all, we've got to calculate the total extension when the 120 Newton weight is applied. So a couple of things. When we've got two wires, that are hung in series with each other, so like this, with a weight, 120 Newton weight on the bottom, both wires will experience that same weight. Okay? Then let's just deal with the area, we might as well. So 3.2 millimeters square. So remember, you can do 3.2 millimeters times 10 to the minus 3. And because it's squared, you just do that again, times 10 to the minus 3, which will give us an area. The 3.2 millimeters squared is 3.2 times 10 to the minus 6 square meters. So I've jot them down. Okay, so let's find the extension of each one. So we're going to use E equals phi, and then rearrange to find the extension. So the extension is force times length divided by Young's modulus times cross-sectional area. So let's do the steel wire first. So extension is force, so 120 newtons, times the length, 0.85, divided by Young's modulus, 2 times 10 to the 11, multiplied by the cross-sectional area, which is 3.2 times 10 to the minus 6. So that gives an extension that's equal to 0.16 millimeters. Then let's do the brass. So the extension is equal to the force, 120, multiplied by the length of the brass, 1.35, divided by the Young's modulus, 1 times 10 to the 11, multiplied by the same cross-sectional area. And let's see what the extension is, this one. So calculate that. So you should get 0.51 millimeters. And if we add those together, the total extension is 0.67 millimeters. Hopefully that went okay. Now let's find the total mass of the combination wire. So make sure that's down. I'm going to remove this. Then let's do the mass. So mass is density times volume. And we've got the density. The densities here. The steel and the brass, 7.9 times 10 to the 3 and 8.5 times 10 to the 3. So we just need the volumes. So let's do the mass of steel first. So mass of steel So we need to do the density of steel, which is the 7.9 times 10 to the 3. Multiplied by the volume. Now the volume is the cross-sectional area times the length. So the cross-sectional area is the 3.2 times 10 to the minus 6, multiplied by the length, which is 0.85. So that gives the mass of steel to be 0.021 kilograms. Then let's do the mass of brass. So the density is 8.5 times 10 to the 3, multiplied by the volume, which is the cross-sectional area times the length. So we need to multiply by cross-sectional area, 3.2 times 10 to the minus 6, multiplied by the length of the brass wire, which is 1.35. So that gives a mass of a brass wire equal to 0.058. 0.058 kilograms. Sorry, 0.037 kilograms. Then we need to add to get the total mass, which is the 0.058 kilograms. Hope that went okay and you found that useful. And if you want to do the questions again, just rewind, attempt them again, check the answers. And thanks for watching, and I'll speak to you soon. Bye-bye.